So our ultimate thing we came up with yesterday was that when f prime was positive, f was increasing. When f prime was negative, f was decreasing. And it works backwards, so if f is decreasing, what do we know about f prime? It's negative. And if we know f is increasing, f prime is positive. But we still didn't come up with a way to tell if something was a local extrema or not. We need to be able to definitively say, this is a max or this is a min. So we're going to compare two things right now. F of x equals x to the third, and we're just keeping it basic so we can compare. F of x equals x squared. We're going to see what happens as we look for where it's increasing and decreasing, and how to tell then if something's a max or a min. So looking at f of x equals x cubed, how do we find where this function is increasing or decreasing? Take the derivative, set it equal to 0. So I want you guys to do x cubed, you guys to do x squared, and you guys to do x cubed. So find where these two functions are increasing and decreasing. It shouldn't be super time consuming. We're just practicing this skill.
Plus or minus? There is no plus or minus. Yeah. Plus or minus. Yeah. Is that right?
So 0's the break point, but then we need to still perform a line test. We need to see what intervals are positive, what intervals are negative. What was our critical point? That was like 1. 0. 1 wasn't a critical point. 1 is one of our test points. So we didn't actually split it into 3 intervals. We just split it into 2 this time. So, Evelyn, will you come write up your intervals of increasing and decreasing for x squared?
Want me to write down the sentence?
No, just increasing from here to here, decreasing from here to here. That's all we need right now.
Sneeze. Oh. I'm gonna go right. I know.
Whoa,
Wait, isn't
it's
it?
Arabic.
You did it backwards.
It's
opposite.
It's
opposite. Oh,
So
sorry.
if you plug in
Switch.
-1 into the derivative,
Oh, just do an arrow.
Little arrows.
My bad.
It's like thinking.
happens. We could also maybe, no, they're attached. Sometimes.
Oh, that'd be cool. How did it know it was attached? Because it's like on the same line.
You guys are right. So Eliana, will you you can write up the intervals where x cubed was increasing and decreasing.
Really? No, I didn't like it.
So after we get these intervals, we're going to look at the graphs now. We're going to see what is the difference between these two things. You cannot rest your hand on the board while you write. You have to only touch the pen to the board.
I didn't know that Evelyn spoke Arabic. She wrote Arabic down.
You're really just
Oh, whoa,
It looks
that's
good
also,
in fish.
no, I think that's more like Chinese. You can see the characteristics.
I feel like we should get Ben up here just so we can make fun of his handwriting. We can all make bets as to what language it will look like. Winner takes all.
Sweet, I totally joined the bet.
I want that.
Can you show me?
Okay, so let's look at the graphs of each of these. So what do we know the graph of x cubed looks like?
I don't know.
It's
I don't know. It's
Oh,
kind
isn't
of
it like?
a stretched out S.
Just kidding.
kind of, I can see that.
Okay,
And
that's what it looks like.
Ben, what's the graph of x squared look like?
Oh, x squared, isn't it just a parabola?
Parabola.
It looks like a U.
Looks like a U. So which of these has an extreme value?
The parabola
The parabola has an extreme value,
has that.
has a minimum.
At 0, 0.
At 0, 0. So we need to see how does the derivative tell us that that's a minimum compared to this where, yes, the derivative here is 0, but it's not a minimum. So let's look at the derivative functions next. What was our derivative function for x cubed? 3x squared. So it's going to be a stretched up parabola. And derivative function for x squared?
It's 2x.
2x. 2 over 1, so something like this. We don't need to be super duper accurate. So what's the difference between our two derivative functions?
One is the name and the other one is a U.
This one actually tells us more cool stuff.
With the U, it's all positive.
With the u, our derivative function is all positive. But here, with our line, we have a piece that's negative and a piece that's positive. So on this one, when we did our line test, when we split it into two sections, we got from positive to positive. But on this one, when we did our line test, but I almost tripped for no apparent reason.
I do that all the time.
Okay?
That was me for over half an hour.
So on this one, what happens when we plug in our test points?
You get negative and positive.
Negative to positive. So that one was no minimum. This one did have a minimum. So what conjecture can we make now? What about the derivative told us specifically that this was a minimum and not just a horizontal tangent line? This is the derivative. This is the derivative.
Has to
Derivative
have a
was,
positive and a negative?
okay, so it had to switch signs. Specifically for a minimum though, what order do we have to switch signs? Negative to positive. Negative on the derivative told us our function was decreasing. Positive on our derivative told us our function was increasing.
Yeah.
So if we had something like this instead, positive to negative, positive would tell us our function was increasing. Negative would tell us our function was decreasing. So it's a maximum. So that gets us the first derivative test. Maybe. Where'd it go? Wow. Oh, okay, that's why. Okay, first derivative check test. If f prime changes from negative to positive at some x value c, it's just saying some specific x value, then f of c is a minimum. I should write this down in your notes.
Good time.
If f prime changes from positive to negative at x equals c, then f of c is a maximum. And if f prime doesn't change sign, it's neither. So again, the reasoning behind that is if f prime goes from negative to positive, what that is telling us about the function itself is that we're going from decreasing to increasing, which gives us a negative value. F prime is going from positive to negative. It's telling us that f is going from increasing to decreasing, which is a maximum. And if f prime doesn't change sign, then we're either going from increasing to increasing or decreasing to decreasing, which is not a max or a min. Okay, so let's do an example. Now notice this example is on an interval, which would make us think, and we're looking for extreme values. I should have put the instructions, but I did not. We're working on an interval, which would make us think extreme value theorem. But what is different about that interval that would not work for extreme value theorem? It's not something. Extreme value theorem had to be on a certain type of closed interval. Is that interval closed?
No.
No. The only reason they gave us an interval is because when we're working with trig functions, we could be getting an infinite number of answers, so we have an interval just so we don't get an infinite number of answers. So we're trying to find, there we go, the extreme values which means we still need to do the same thing we were doing with extreme value theorem in that we do need to find the critical points. With extreme value theorem, then we ended completely different. Then we took the endpoints and the critical points and plugged them into f of x. But with this one, we're going to have to plug stuff into f prime of x. We're only going to be using the test points in f prime of x so that we can see what our actual function is doing. So we take the derivative, set it equal to 0. Derivative of 1/2 x, that's easy. 1/2 minus cosine x. And we're trying to see where that equals 0 or where that does not exist. Does cosine have any values where it does not exist? Think of the graph of cosine. No, it's continuous everywhere. Tangent, on the other hand, you know where it goes down asymptote, down, asymptote.
And every pi half says it.
But cosine and sine, those are continuous everywhere. So we don't have to worry about does not exist, but we do have to worry about the values between 0 and pi where it would equal 0. So I'm going to add cosine x over. And then we're trying to figure out what x is. So again, we have to get rid of cosine. And what's the only possible way to get rid of cosine? Inverse cosine. So we want inverse cosine of 1/2. We want to know the values where cosine is 1/2. So we have to think back to our unit circle. Sometimes I actually write out my unit circle because I can't seem to ever remember it. But we really just need one quadrant, and then we could find the rest of the quadrants. So we know 30, 45, 60. We know they're all over 2. And then all we have to do is count. We start, I always get this mixed up, but I think we start on the right side. 1, 2, 3. 1, 2, 3. And then it's square root on the top of each of them. But what's the square root of 1? 1.
Why didn't we know this? Why did Mr. Kennedy learn this?
I barely showed Miss McDonald because someone in ACT prep was like, "Why didn't Miss McDonald show us this?" And I didn't know it when I first started teaching. So just randomly, sometimes you come across information, cool little tricks about how to memorize things.
This would have made it
This
so
would-
much
I would have actually learned
easier.
like if they actually.
Oh my
So
goodness.
she knows now.
Yeah.
So
There we have it easier now.
yeah.
That's easier.
So once you get this part, you can just flip it across to find the rest. But when you flip it, so like this value would go with the top one of the unit circle over here. So it's still square root of 3 over 2 1/2.
It's just.
The first one is negative. So you can just flip it across, you can flip it down to see where all of them match. So we go cosine sine. So which of these is 1/2 for cosine? The first one, which is 30 degrees, or pi over 6.
Yeah.
We do need it in radians. So x is pi over 6. And we need this to still be positive, so we want to know on the other side here.
According to my chart, you have it backwards.
I do? Did I count it the wrong way? I always
It's
count
1/2, then square root of 3 over 2.
I always forget where to start counting. Dang it. Sorry, guys. Okay, so we start counting on the left. I always mix that up. I don't know why. 1 over 2. Square root 2 over 2. Sorry. Now you're all going to remember it backwards. Start counting on the left.
Read like right, left to right.
Okay, so we read left to right, so we start counting top left.
Down.
And then go down.
Ooh,
And then
like
back
a
up.
parabola.
Okay. So it's pi over 3, not pi over 6. Thank you for checking, Ben. I always do that backwards. But still, we want this x value to still be positive, so which way should we fold it to make it positive still? Which way, if I fold it this way, will our x value still be positive?
Oh.
Fold it down. So we want this value that's negative 60 degrees.
5 pi thirds.
Yeah, but we're never going to remember that this is 5 pi thirds, so I'm doing the long way. Degrees, what would this angle be then positive-wise? If we, 300, 360 minus 60 is 300. And how do I switch 300 degrees to radians?
U times pi
Pi over
180.
So reducing, we get 5 pi over 3. There's also kind of a trick to remembering radians, but I think it's almost quicker that way than building the whole unit, because with the radians, you have to build the whole unit circle in radians to make the trick work.
Or I just thought 2 pi and then just minus 1.
True. 2 pi minus pi over 3. That would have also worked. So we have x equals 5 pi over 3. And then we still perform our line test, but this time we're looking for something different as our answer. Now because we're on a closed interval, because we're on an open interval, but we're on an interval, we don't have to worry about anything to the left of 0 or to the right of 2 pi. We go pi over 3, 5 pi over 3. And now again, where we're in radians, it is going to be a little bit harder to pick values that we plug in. We won't have this problem unless we're doing a trig interval. So we need something between 0 and pi thirds. It has to be smaller than pi thirds. So I always think of the fractions again and I ignore the pi. What's smaller than 1/3?
1/4.
1/4. So let's pick pi over 4. That's our test point. So again, these are our critical points. If it helps, circle them so that we know what we're looking at. Okay, so then we have to decide what's between 1/3 and 5/3.
4.
4/3. Or, what could make it even easier,
1/2.
I was thinking 3/3, because that's 1.
1/2 third.
1/2 would also work. But I was thinking 3/3, because then we get 1 pi as our test point.
Nice.
What about 5 pi over 3 to 2 pi? Now this is where, again, I might change it to, well, no, so if I change this to over 3, that's 6 pi over 3. That's 5.5 pi over 3. So we can just increase the fraction again. What if I multiply both by 2? 10 pi over 6 and 12 pi over 6. Now what's between the two?
11 by 6.
11 pi 6. So I think of it more in terms of the fractions than in terms of radians. I just say, hey, between 5/3 and 2, so 11 pi over 6. So now we plug these in. What do I plug this into? So we did critical points first. We did line test. And we plug the test points into f prime of x. So the key to remembering the difference between extreme value theorem and first derivative test is extreme value theorem, we were plugging the critical points into f of x. In this one, we're plugging test points around the critical points into f prime of x. So to save us some time, you guys plug pi over 4 into f prime of x. You guys plug pi into f prime of x. And you guys plug 11 pi over 6 into f prime of x.
11 pi 6 in the f prime of x.
Yep, whatever f prime of x was, I can't see there. It's like 1/2 minus cosine x.
Yep.
So just to tell us whether we have positive or negative, that's all we're looking for.
Neutral. It's neat.
And make it 0.
I actually got one at lunch that was 0, and then I realized I put it wrong.
Then you plugged in the critical point.
Yeah.
You got 3/2,
Yeah.
so positive 4 pi. Okay. So do you control enter to see what that is as a decimal?
That never works for me. I always like just re-enter it against once.
Okay, so negative over here. And
Negative.
negative over here. So again, on the AP test, this line test is a way to organize our information. It is not a way to actually answer our question. We need to make a conclusion now. I need to state what was my max, what was my min. So, pi over 3. Is that where our max is located or our min is located? If we go from negative to positive, our function is going from decreasing to increasing. So we have a minimum. So we have a min at pi over 3. So what about 5 pi over 3? Is that a minimum or a maximum? Maximum. Max at 5 pi over 3. So, again, it depends on what I ask you to find, or what they ask you to find. If I said, where is my minimum, where is my maximum, we're done. What if I said, what is my minimum, what is my maximum? If I know this is where the minimum occurs, what would we do with this to find what? Plug it into f of x. Min at pi over 3 is whatever f of pi over 3 is. Max at 5 pi over 3 is whatever we would get when we plug in 5 pi over 3. So being able to perform the first derivative test is a key component of the AP test. This is a major thing, not a minor thing. This is you will not get a 3 if you don't know how to do this. So we need to be very solid on this, and I wanted to practice some more AP problems. So we're actually going to stop there, and we'll have about half an hour-ish to work. And today I have a worksheet only.